All right, welcome back. Hopefully you did the counting on these pyramids. Again, they're called pyramids because they all come to a point up here at the top instead of a prism where they have a polygon on their top. So on these pyramids, and compare it to the chart that I have there. I'm going to run through each one of these just to make sure you understand where everything comes from. The first one is a triangular pyramid, and it's called triangular because all the sides are triangles, and the base is a triangle. And that's really the reason it's more the base is the reason it's called a triangular pyramid. Pyramid becomes it comes to a point, and triangular pyramid because the base is a triangle. It has 4 faces. The faces that go around the outside, all the way around, so it's 1, 2, 3, and then the one on the bottom, so that makes 4. On the vertices, if you count each vertex, each point, there's 3 around the base and 1 at the top, so that makes 4. And then finally, edges, there are 3 edges around the sides, and then 3 edges around the base, and 3 plus 3 is 6. Next one is a rectangular pyramid. It's called rectangular because the base is a rectangle. It has 5 faces. If you count each of these faces, or as you go around, there are 4, and then you have 1 on the bottom. So 4 plus 1 is 5 faces. On the vertices, we have 1, 2, 3, 4, and then 1 at the top. That makes 5. And then edges. 4 edges around the sides that are going up to the peak, and then 4 edges around the base. 4 plus 4 is 8. Next figure has a pentagon as a base, 5-sided figure, so it's called a pentagonal pyramid. Faces on this one, if we start counting all the way around, there are 5 faces, and then we have the one on the bottom. 5 plus 1 is 6. Notice the same number of sides on that pentagon on the bottom is how many faces this pyramid will have. They do go together. Vertices. Let's see. Let's count those vertices. I have 1, 2, 3, 4, 5 around the base, and 1 at the top makes 6. And then edges. 5 edges around the sides that are meet at the peak, and 5 edges around the base. 5 plus 5 is 10. And last but not least, hopefully by now you're kind of seeing the pattern and how things work. We have a hexagonal pyramid. Hexagonal because the base is a hexagon. It has 6 faces as you go around, and then the one on the bottom. 6 plus 1 is 7. As far as the vertices are concerned, we're going to have 1, 2, 3, 4, 5, 6 around the base and 1 at the top, so that makes 7. And then edges, 1, 2, 3, 4, 5, 6, and around the base 6 more. 6 plus 6 is 12. Do you see a pattern? If we add the number of faces and vertices and compare it to the number of edges, look back at the other chart that we made. Did you notice a similarity? There are 2 more edges than there are, if you add 2 to the edges, you get the sum of the faces and vertices, just like we did on the prism. So it doesn't matter if you have a prism or a pyramid. If you add the number of faces and vertices together, it will be 2 more than the number of edges. And folks, this is something called Euler's formula. Euler was a mathematician that lived a very, very, very long time ago. And he discovered this relationship, just like you did. Well, I'm sure that he looked at a whole bunch more solids than we even did. And not just prisms and pyramids, but there's some more figures here right below. Some other kinds of polyhedron. But Euler's formula says the number of the faces, that's F, and the vertices, sum means add, is 2 more than the number of edges. And that stays consistent no matter what kind of polyhedron. Nice thing about that is then as these get more complex, we don't have to do all the counting. We can do some calculations if we know part of these. For example, the polyhedron on the left, made up of a whole lot of regular 2, 3, 4, 5 pentagons, made up of a whole lot of regular pentagons. We don't know how many faces there are, but using Euler's formula, we can make that calculation because we do know some of them. We know that there are 30 edges, so I'm going to put that in for E. And we know that there are 20 vertices. Well, look at that. That's a pretty simple algebraic formula, isn't it? Or algebraic equation. F plus 20 is 32. And if you subtract the 20 from both sides of that equation, we find out that the number of faces is 12. If we had the solid, we could turn it around in our hands and count it. But if we know 2 of those pieces of information, we can find any of the third. Okay, let's do this one more time. Let me write down Euler's formula. And I would suggest that you do that every single time. And then substitute the numbers you know. We have 20 faces. We have 12 vertices. We don't know how many edges. Let's simplify what we know, and we have a very, very simple algebra equation, don't we? Subtract 2 from both sides, and we find out that in this particular figure, made up of a whole bunch of regular triangles, we have 30 edges. All right, that's it for today, folks. It's not really anything too difficult. The counting can get a little tricky, but in your assignment, I'm going to have you look at some pictures, count numbers of edges, faces, vertices, and then I'll be having you use Euler's formula, just like we did in these last 2 examples, to take 2 pieces of information and find the third. Your assignment is posted on Canvas. For those of you who will be in class or who were in class, you could pick up a paper copy. Though if it refers to a colored picture, I think one of them says count the red faces. You're going to have to look at it on Canvas to know which ones are red.